Imagine a place where gravity reigns supreme. Stars are torn apart. Planets are crushed into oblivion. Even light cannot escape the immense gravitational pull. This is the realm of black holes, some of the most fascinating and mysterious objects in our universe. Black holes are regions of space-time where gravity is so strong that nothing, not even light, can escape their grasp. They are formed when massive stars collapse at the end of their lives. This collapse creates a singularity, a point of infinite density and zero volume. The boundary around a black hole beyond which escape is impossible is called the event horizon. Once something crosses the event horizon, it is forever trapped within the black hole's gravitational grip. Black holes are cosmic abysses, relentlessly pulling in matter and energy from their surroundings. But what happens to the information about the objects that fall into a black hole? This question lies at the heart of the black hole information paradox, a profound puzzle that has baffled physicists for decades. The black hole information paradox is one of the most intriguing problems in modern physics. It arises from a fundamental conflict between two of our most successful theories, Einstein's general relativity and quantum mechanics. General relativity describes the universe on the largest scales, explaining the behavior of gravity and the formation of black holes. Quantum mechanics, on the other hand, governs the microscopic world of atoms and subatomic particles. It tells us that information cannot be destroyed, only transformed from one form to another. This principle of information conservation is fundamental to our understanding of the universe. The paradox arises because classical black holes, as described by general relativity, seem to violate this principle. When an object falls into a black hole, it appears to be lost forever, along with all the information it carries. This loss of information contradicts the fundamental tenets of quantum mechanics. The black hole information paradox is not just an esoteric problem for theoretical physicists. It challenges our understanding of the very nature of reality and the limits of our knowledge. Solving this paradox could revolutionize our understanding of the universe and its fundamental laws. To grasp the essence of the black hole information paradox, we must first delve into the nature of black holes themselves. These mysterious entities have fascinated scientists and the general public alike for decades, and understanding them is key to unlocking some of the universe's deepest secrets. Black holes are not empty spaces, as their name might suggest. Instead, they are incredibly dense regions where the gravitational pull is so strong that nothing, not even light, can escape from them. Instead, they are cosmic monsters, regions of space-time where gravity is so intense that it warps the fabric of the universe. This warping effect is so powerful that it can distort the light from stars and galaxies that pass near the black hole. Einstein's theory of general relativity provides the framework for understanding these enigmatic objects. His groundbreaking work revolutionized our understanding of gravity and space-time. General relativity tells us that gravity is not a force in the traditional sense, but rather a curvature of space-time caused by the presence of mass and energy. This curvature affects the motion of objects, bending their paths as they move through space. Imagine a bowling ball placed on a trampoline. The ball creates a dip in the trampoline's surface, much like massive objects create a curvature in space-time. This analogy helps us visualize how gravity works in the context of general relativity. Black holes are formed when massive stars exhaust their nuclear fuel and can no longer support themselves against their own gravity. This process often culminates in a spectacular supernova explosion, leaving behind a dense core. The star's core collapses under its own weight, creating a singularity, a point of infinite density and zero volume. This singularity is the heart of the black hole, where the laws of physics as we know them break down. The gravitational pull of the singularity is so strong that it creates an event horizon around it. This boundary marks the limits of the black hole's influence. The event horizon is the point of no return. Once an object crosses this boundary, it is irrevocably drawn into the black hole. Once something crosses the event horizon, it can never escape the black hole's gravitational pull. This includes everything from stars and planets to light itself. not even light, the fastest thing in the universe, can escape from beyond the event horizon. This is why black holes appear black. They emit no light that we can detect, making them invisible against the backdrop of space. Section 4. Hawking radiation. The evaporation of information. For many years, black holes were thought to be inescapable cosmic traps, swallowing everything that crossed their event horizons and leaving no trace behind. These enigmatic objects were considered the ultimate devourers, consuming stars, planets, and even light itself, rendering them invisible to the outside universe. However, in the 1970s, physicist Stephen Hawking made a groundbreaking discovery that shook the foundations of black hole physics. His work introduced a new perspective on these mysterious entities, challenging the long-held belief that nothing could escape their grasp. Hawking showed that black holes are not entirely black after all. Contrary to their name, they emit a faint glow, a subtle but significant revelation that changed our understanding of these cosmic giants. They emit a faint thermal radiation, now known as Hawking radiation, due to quantum mechanical effects near the event horizon. This radiation is incredibly weak, making it difficult to detect, but its existence has profound implications. This radiation arises from the creation of virtual particle-antiparticle pairs near the event horizon. These pairs are a direct consequence of the strange and counterintuitive nature of quantum mechanics. According to quantum mechanics, empty space is not truly empty, but rather teeming with virtual particles that constantly pop in and out of existence. This seething quantum foam is a fundamental aspect of the universe at the smallest scales. These virtual particles usually annihilate each other almost immediately. However, the presence of a black hole's immense gravitational field can disrupt this process. Near the event horizon of a black hole, one particle of the pair can fall into the black hole while the other escapes as Hawking radiation. This escaping particle carries away a tiny amount of energy from the black hole. Hawking radiation has profound implications for our understanding of black holes. It suggests that black holes are not eternal and unchanging, but dynamic objects that can lose mass and energy over time. Since the radiation carries away energy from the black hole, it suggests that black holes can slowly evaporate over time. This gradual loss of mass and energy could eventually lead to the complete disappearance of the black hole. However, this evaporation process poses a significant problem for the principle of information conservation. In quantum mechanics, information about a physical system is never lost, but the evaporation of black holes seems to challenge this principle. If black holes evaporate completely, what happens to the information they swallowed? This question has puzzled physicists for decades and remains one of the most intriguing mysteries in theoretical physics. Hawking's initial calculations suggested that the information is lost forever, contradicting the fundamental principles of quantum mechanics. This led to a heated debate and numerous attempts to resolve the paradox. This apparent paradox is the crux of the black hole information paradox. It challenges our understanding of the universe and the laws that govern it, prompting ongoing research and new theories in the quest to uncover the truth. Section 5. Quantum Mechanics, the universe's rulebook. This section delves into the intricate and fascinating world of quantum mechanics, a cornerstone of modern physics. To understand why the loss of information in a black hole is so problematic, we need to delve into the realm of quantum mechanics. This field of study reveals the underlying principles that govern the smallest particles in the universe. Quantum mechanics is a revolutionary theory that governs the behavior of matter and energy at the atomic and subatomic levels. It challenges our classical understanding of physics and introduces a new way of thinking about the universe. It is a probabilistic theory, meaning that it can only predict the likelihood of certain outcomes rather than providing definitive predictions. This probabilistic nature is encapsulated in the concept of wave functions, which describe the probabilities of a particle's position and momentum. One of the fundamental principles of quantum mechanics is the conservation of information. This principle is crucial for maintaining the consistency and predictability of physical laws. This principle states that information cannot be created or destroyed, only transformed from one form to another. For instance, when particles interact, the information about their states is preserved even if it changes form. In other words, the total amount of information in the universe remains constant. This constancy is a bedrock of our understanding of physical processes and the evolution of the cosmos. This principle has profound implications for our understanding of the universe. It suggests that the universe operates in a way that preserves the integrity of information across time and space. It means that, in principle, we can trace the history of every particle in the universe back to its origin. This ability to trace particles back to the Big Bang provides a powerful tool for understanding the early universe and the fundamental forces at play. It also suggests that the future is not predetermined, but rather a vast tapestry of possibilities. Each quantum event opens up a multitude of potential outcomes, creating a universe rich with potential and uncertainty. The loss of information in a black hole would violate this fundamental principle. Black holes, with their immense gravitational pull, challenge our understanding of how information is preserved in extreme conditions. If information is truly lost when it falls into a black hole, it would mean that our understanding of the universe is incomplete. This loss would imply that there are aspects of the universe that elude our current scientific framework. It would also have profound implications for our understanding of time and causality. The relationship between cause and effect, and the flow of time itself, could be fundamentally altered if information is not conserved in black holes.